Hi, I'm Deidre Mangan from Memphis, Tennessee, Our Lady of Perpetual Help Catholic Schools, and this is NASA Now.
What that does on the asteroid, does the astronauts read out the gravitational effect of those planets.
Hi, I'm Matt. In today's show, you're going to meet 3 NASA experts who all have one thing in common: engineering. We'll learn about the unique projects they're working on and how science, technology, engineering, and mathematics played a key role in their path to NASA. That's ahead. First, here's what's happening at NASA Now.
Launching a satellite the size of a coffee mug. During the recent launch of the Antares rocket, NASA successfully delivered a trio of PhoneSat nanosatellites to low Earth orbit. The goal of this project, known as PhoneSat 1.0, is to lower the cost of building a reliable space satellite. In fact, the total cost of the components for each satellite is only about $3,500. Approximately the size of a coffee mug and weighing less than 4 pounds, each of these easy-to-build satellites is made extensively of commercial, off-the-shelf components, including an unmodified consumer-grade smartphone. While in orbit, these satellites are expected to send back digital images of Earth and space using onboard cameras, as well as information about the satellite's health.
From lasers to drop tests to aerobraking, our experts use some of the same principles, theories, and approaches you're learning in school right now. You're going to hear from 3 different engineers who will share a little bit about the missions they're working on and the secret to their success.
I'm an aerospace engineer here at NASAâs Langley Research Center. I work on planetary exploration missions that use the atmosphere to fly through to slow down the spacecraft to safely reach either the surface of the planet or to safely achieve a circular orbit around the planet. Aerobraking has been used at 4 different missions so far. The first one was Magellan at Venus, and the second, third, and fourth missions were all at Mars. Aerobraking is very much like if you had 2 very large arms and stuck them out the sides of your car windows, and if your arms were large enough, they could maybe slow down your car. And it's very much the same principle as what we use at Mars. The spacecraft have 2 very large arms, or solar panels, and they put them right into the flow of the wind so that they drag the spacecraft through the atmosphere. I was a physics major in college and was unsure of what path I wanted to take. So I decided to undergo more school, and I decided to do graduate school at George Washington University, which was located here at NASAâs Langley Research Center. And it was my first experience with engineering, but I was put into such a wonderful field where the first thing I did was work on aerobraking orbiters. And it's something I immediately loved and decided to stick with it.
I'm working on a SENS, which is an atmospheric remote sensing system that eventually will be put in space to monitor greenhouse gases such as CO2, to monitor global winds, which gives us a better ability to predict the weather and climate patterns. If you're trying to measure CO2 or ozone, the light wavelength or color that molecule or element responds to is different. So we design and develop laser systems to produce enough power in the right wavelengths that would allow us to actually make the measurement. And that's of course more challenging when you're trying to make that measurement from space, because it requires more powerful systems where power is one of your limiting factors. You can't exactly stretch an extension cord all the way up to the space station. For me, the path was a very diverse one. I always enjoyed math and science. Wasn't really sure what I wanted to do though. I started out actually attending college, studying mechanical engineering technology. I was fortunate enough to get into a technician training program here at NASA. I worked as a technician for a number of years and really developed an interest and a skill and aptitude for working on laser systems.
My current project is on the Orion multi-purpose crew vehicle landing test for water impact. The Orion program, much like Apollo, initially wanted to have a land landing, and we were conducting land landing tests. Basically, because of weight constraints, it's actually much easier to design a system that will land in the water. To conduct a test, we have a hydro impact basin. It was filled with approximately 1 million gallons of water. It's 20 foot deep, it's 115 foot long and 90 foot wide, and it allows us, with the use of the gantry, to simulate the velocities that the Orion crew module would have upon splashdown in the ocean. I always had interest in how things worked. I used to love to take apart things. I had an interest in gears, in small engines, and also in nature and understanding how mankind has designed and how we've mimicked nature in many cases.
Now that you've seen how engineering plays such a critical role in aerospace and aeronautics, here's a chance for you to test your engineering design skills in this challenge.
Teachers, you and your students can work on a project involving the Orion Multipurpose Crew Vehicle. Look for Real-World Mathematics, Preparing for a Soft Landing under the Extension Activity tab on the NASA Explorer School's virtual campus.
Well, that's it for NASA Now. Be sure to visit our Facebook page and leave a comment. We'll see you next time on NASA Now.
NASA Now comes to you from the virtual campus at NASA Explorer School.